A very good morning to my respectful lecturer, Dr. Isham. Today we're going to explain about electrical machine project. We are from section 1, group 7.
My group member is Kartiva Armugam, Ahmad Akram Azfar, and Hafzalham bin Muizzuddin. Okay, for the introduction, this report focus on determining circuit model parameters for a three-phase induction motor, a critical task in understanding motor behavior under varying loads. By conducting tests such as the DC test, block rotor test, and no load test. The motor resistance, impedance, and reactance are measured and analyzed. Using MATLAB and simulating models, these tests simulate real-world conditions, providing valuable insight into the motor efficiency, losses, and performance characteristics. The study underlined the importance of electrical machine in modern technology, particularly in industry like automotive and heavy machinery.
Okay, now I'm going to explain the methodology part. The methodology for this project is involved performing several key tests on the three-phase induction motor using MATLAB simulation. The process I include three-part DC test and then block rotor test and then no load test. For DC test, apply a DC voltage to measure the stator resistance, and then block rotor test is clamp the motor shaft and connect the three-phase supply. So it will be inject the three-phase supply to determine the rotor impedance and resistance. So next is no load test. In the no load test, allow the motor to run at the no load. So and measure the magnetizing reactance, copper loss, and then the rotational loss also. And then torque speed characteristics, stimulate analysis torque speed relationship and motor efficiency. And each test require careful steps, simulation, and analysis with the manual calculation also. Okay, now I'm going to explain about the test one. In test one, these are the circuit. This is a test circuit for the DC resistance test. In this circuit, there are four questions. Develop a simulation model of three-phase induction module using Stimulink in the MATLAB software. So we need to construct in the MATLAB software. And then select the assignment type of asynchronous machine for each group. Our group is group 7, so we are using 7 asynchronous machine. And then run the module for 10 seconds and record the result of IDC and VTC. So at the end of the stimulation, we will get IDC and then VTC, and then calculate the stator resistance R1. So we need to calculate R1 by using the IDC and VDC. In this test point, basically the DC voltage is applied to the stator winding of the three-phase IM because the current is in DC. Therefore, no induced voltage in the rotor circuit, and then no result rotor current. And then the reactance is zero because the current is like a direct current. Okay, move on to next is I will explain the calculation part and then the simulation part. Okay, now I'm going to explain about the calculation and simulation part for the test one. For first, I explain the simulation part. In simulation part, this is the circuit that I construct in the MATLAB software. There have input voltage 5 voltage. There have asynchronous mission number 7, and then therefore no load. The constant is equals to 0, so without any load. And then the upper display are showing the current 139.5 ampere. And then there have three resistance that I put 80,000 ohm, and then it will be there have three resistance over there. So these are the stimulation that I construct in the MATLAB. After I explain the calculation, I will explain again the circuit part, and then the calculation part we need to find the R1. So I use R1 equals to VDC. VDC over 2 times IDC. VDC we already know 5 voltage, and then 2 times, and then we already get IDC 139.5, and then we will be get 0.0179 ohm. In this DC test for three-phase induction motor, the method are measure the stator resistance of the motor. In this test, the DC voltage is applied the stator winding, which allow the calculation and then resistance without interference from the reactance, which only occur with the alternative current. The main objective, the DC test, is measure the stator resistance in three induction motor. When the direct current is applied to the stator winding of the three-phase induction motor, only the resistive component stator wind comes into the play. And then the rotor is stand still because there are no induced uh, electromotive force in the rotor. So if the DC is DC voltage is applied also, therefore no any any of the changes in the machine because the constant is equals to zero. And then next is in a Y connected stator winding. Just now we see in the circuit there have a Y connection, and then the DC applied between the 2 and 3 terminal, allowing the current flowing through the stator winding. The relationship between the applied DC voltage and then the current IDC is by the Ohm's law. So we're using the Ohm's law to find the R1, and then this R1 we will be used in the test 2 also. So after that, in the test 2 I will show how we use the R1 in the test 2, and then finally a high stator the resistance index more the power losses. So I will the power losses everything in the test 2. So for test 1, these are the important thing in the test 1. Okay, now I'm going to explain about the test 2. It's called block rotor test of three-phase induction motor. In this test, objective is to measure the value of total impedance ZLR, and then log the rotor resistance RLR, and then log the rotor reactance XLR with respect to the stator of three-phase induction motor. There are for six questions in this test. So I will explain the stimulation first, and then I will explain the calculation in next one. Okay, now I'm going to explain about the test 2 circuit. These are the test 2 circuit. They have a induction motor, the S recognize machine, and then in this machine, the have a constant is equals to zero. Because the motor is not run, we can see the rotor speed is equal to zero. Then only we can measure the value. V phase, I phase, and V synchronize, and then there have a VRMS in front over there. So we will edit. We are using 1 voltage to 5 voltage. We need to find the I phase, V phase, and then power SC for each and every voltage 1 until 5. So these are the procedure for this test 2. Uh, and then for this test, the motor shaft is claimed so that it cannot turn. The motor terminal are connected to the three-phase supply. Just now I say so. The rotor become the secondary of the transformer operating at the supply frequency. So the block rotor test is similar to the short circuit test of the transformer. So it's performed calculate the series parameter of the induction motor. Its leakage impedance. The rotor is blocked to prevent rotational and then balance voltage applied to the stator terminal where the rate of current is achieved as shown in the figure over there. And then under the reduced voltage condition, and then the current core and the current core loss, and then magnetizing component of the current are quite small percent of the total current. So on to next is the table part over there. So observe data for three-phase induction motor for block rotor test. For voltage 1, V phase 1, we get 8.205 I phase, and then P SC is 5.645. Uh, and then for voltage 2, 16.41 ampere, and then 22.58 watt. And then for voltage 3, 24.61 ampere, and then 50.82 watt. And then for voltage 4 32.81 ampere, and then we get power 90.33, and then for voltage 5 we get 4103 ampere, and then for power is 141.2. So move on to next is the calculation part. Okay, now I'm going to explain the calculation part for test 2 block rotor test of three-phase induction motor. First, we calculate for V max equals to 1. So, we already get V phase equals to 1, I phase equals to 8.205, and then power synchronous is 5.645. First, we need to find voltage for line. So, there a formula voltage phase equals to voltage line over square root 3. So, we just substitute the value, and then we will get voltage line equals to 1.7321 voltage, and then the voltage line is equals to voltage total. So in this induction motor, so the in this induction motor, I phase equals to IL. So we already get the I phase, so IL equals to 8.205, and then we need to change into I synchronous current in synchronized. So there have a formula for that. So high phase times with 220 over V phase, and then we substitute the value, we will get 1805.1 ampere. And then now we going to find the uh, going to find the power factor. Before that, we need to understand power in is equals to power synchronized. So there are a formula square root 3 V total IL cos theta. So we just substitute the value over there, and then because we need to find the theta, so we need to substitute the value, and then we change, and then finally we get the theta equals to 76.74 degree. And then now we're going to do ZLR. We already have V phase and then I phase, so we just substitute the value, and then we will get 0.1217. Okay, now we need to find R2. So R equivalent equals to RLR. So we already get R1 in the first test 0.01719. So we need to minus with the 0.0280, and then minus with the 0.019, we will get 0.0101 ohm for R2, and then we will get the X1 and X2 equals to 0.3187 over 2, we will get 0.0594. So ZLR, we should have the formula ZLR cos theta plus JZR sin theta. So we already get ZLR 0.1219 cos the theta. Just now we get 76.74, and then plus with the ZL again 0.1219 sine, and then theta again 76.74, and then we do the solution, we will get ZLR equals to 0.0280 plus J 0.1187. So in this formula, we will find RLR equals to 0.0280, and then ZLR equals to 0.11870. So now we're going to find the power for the stator. So power for the stator, the formula is 3 I phase square times with R1. We already have the R1, and then we substitute the value, we will get 3.6152 watt. And then the another stator for PCU is equals to uh, equals for the rotor. Now we're going to calculate the for the rotor, and then PSC equals to PCU stator. Just now we calculate 3.6152. So we just substitute the value, and then we will get 2.0297. So these are the for voltage maximum equals to 1, and then the same method we're going to use for voltage maximum equals to 2. Voltage maximum equals to 2, the voltage phase is 2 voltage, I phase equals to 16.41, power synchronized equals to 22.58. So we find the same method, same formula in this also. So we will get voltage line equals to 3.46 4641 voltage, and then we will get I synchronized is 1805.1 ampere, and then we get the theta is the same theta we already get in the maximum value equals to 1. So same theta we will get over here 76.74. You should be get the same theta, and then the same method you are going to use over here. We need to use the ZLR formula, and then we substitute the value, and then we will get the RL and XLR, and then we should find the power stator by using the same formula 3 I phase square R1. So we just substitute the value over here, and then PCU stator is equals to 14.4608 watt. For the rotor, we already have PCU minus with the PCU stator, So we just substitute the value, we will get 8.1192 watt. Okay, now is voltage maximum equals to 3. So the same formula, same way we are using for before this, voltage maximum equals to 2, voltage maximum equals to 1. The same thing we are going to use for voltage maximum equals to 2. In voltage maximum equals to 2, V phase equals to 3 voltage, I phase equals to 24.61, and then power synchronized is 50.82. The same thing we are going to use over here, same formula. And then we get VL equals to 5.1962 voltage, and then we will get current synchronized is 1806.9333 ampere, and then we get the theta equals to 76 the 0.74, and then ZLR equals to 0.1219, and then in ZLR we use the same formula over there, and then we will get R and then XLR 0.0280, and then XLR equals to 0.1187, the same impedance we get before, and here also same. And then uh, we calculate the PCU for stator, we will get 32.5235 volt, and then the same formula we use for PCU stator, and then we will get 18.2965 watt. And then move on to next is voltage maximum equals to 4. For voltage maximum equals to 4, the voltage phase is 4 volt, I phase equals to 32.81, and then power synchronized is equals to 90.33. And then the same formula we are using over here. So voltage line equals to 6.9282 voltage, and then I synchronize equals to 1804.55 ampere, and then theta is the same value 76.74, and then ZLR equals to the same value 0.1219, and then the ZLR also the same value, because in here the impedance are in same impedance. The voltage are getting different, current are getting different, but the imprints are still in the same thing. Okay, so RLR equals to 0.0280, and then XLR equals to 0.1187, and then PCU stator is we using the same formula, and then we substitute the value, and then we will get 57.8078. So the power are getting higher for stator and rotor, and then the rotor equals to 32.52 watt. Okay, now I'm going to explain about the last Vmax equals to 5. So in Vmax equals to 5, V phase equals to 5, I phase equals to 41.03, P synchronized equals to 141.2 watt. And then we using the same formula here, and then VL equals to 8.6603 watt, and then I synchronize equals to 1805.32, and then the theta equals to the same theta 76.74, and then ZLR equals to same 0.1219, and then from there we use the formula, and then we will get RLR 0.0280 same, then SLR equals to 0.1187, and then we use the same formula over here. We find the PCU stator equals to 90.40, and then PCU rotor for 50.80 watt. In this calculation, everything we can analyze the reveal that RLR and XLR remain the steady, the power factor stabilize, and then the line current increase with the voltage. In this circuit analyze indicate the equivalent circuit behave similarly to a transformer exhibiting minimal core of magnetizing losses. Overall, the calculation display in the linear relationship between the voltage and current with the consist impedance characteristic confirm the motor starting characteristics. And then the valid theoretical prediction of the log rotor condition with the total impedance maintained at the 0.1219 ohm. And then the complex impedance we already see 0.080 plus 0.1187 ohm. And then the phase angle of the approximately 76.74 theta, theta value. The input power increase quadratically with the voltage, and then the power distribution confirm the linear increases in the both stator and then the rotor copper losses indicate the step successfully verification of the balance three phase operation.
For a test 3, the procedure is develop a simulation model of three-phase induction using Simulink in MATLAB software. Second, select the exact type of conditional machine, uh, which is 50 Hz or 60 Hz based on the select. Third, set the Vmax to nominal voltage 220 volt and run for 100 seconds. For observe the Vpace, Ipace and PSC value and record the result and do a calculation for a procedure that we give. Okay, for a simulation, represent the simulation of asynchronous induction machine in MATLAB. Simulink showing key inputs, output and performance parameters. The motor is powered by a three-phase voltage source with an RMS value of 220 volt per phase, which is the standard input for industrial motors. The motor generates an electromagnetic torque of 7.52 Newton meter, which represent its ability to drive a mechanical load. The rotor speed is shown as 1000 rpm, slightly below the synchronous speed, which is typical for induction motor. Key performance metrics include an RMS current of 29.13 current, showing the electrical load and power loss of 1.472 watt, indicating efficient operation. This value demonstrates that the motor is working within its design range with stable voltage, current, torque and speed. Okay, for a calculation, it's related to the performance of an induction motor. It focuses on three key aspects: total impedance, stator copper losses and rotational losses. First, total impedance ZAQ. Impedance is calculated using the formula ZAQ, where phase voltage is 219.3 volt and phase current is 73.33 current. The result is ZAQ equal to 2.987 omega, which represent the motor resistance to current flow. Second, stator copper losses. These losses occur due to resistance in the stator winding and are calculated as using R1 equal to 0.01812 omega and the stator copper losses are 293.78 watt. Last, rotational losses. Rotational losses including friction and core losses are found by subtracting stator copper losses from the total power consumed. This gives P root equal 1472 minus 293.78 equal to 1178.22 watt. Thank you.
Okay, hello. Assalamualaikum. My name is Abdulham bin Muizuddin. And after test 3, I want to continue about test 4. Okay, about test 4 is about develop a simulation model of three-phase induction model using Simulink in MATLAB software. Second, select the assigned type of a synchronized machine for each group and set the frequency either 50 Hz or 60 Hz based on the selected synchronized machine. Okay, number 3 is run the simulation. Number 4, find the slip at the pull out torque and find the value of the pull out torque itself. Number 5 is sketch the per phase equivalent circuit of this motor based on the result obtained from all the tests and measure the efficiency of the induction motor. Okay, first of all, I want to develop the circuit, and then I want to add on the graph at the behind of the circuit, and then I select the frequency, which is frequency is Malaysia is give, and I am the group 7, and then I want to use that frequency, and then I run this circuit. Okay, I continue about the simulation. What the simulation circuit it's the same with another test. Test 1, test 2. The difference between another test and this test is we add on the graph, SY graph, and then that's it, and then we can get the value V line, I line, and PSC. Okay, for the V line we get 382.3, I line we get 1857, then PSC 1.429 E plus 06, and then I will explain about the graph. So the graph is what we can see at the graph is the peak of the voltage. Okay, the peak at the peak of the that RMS value is the T max there. What is the T max? T max is the value of the T max is 1378.8. That's it. That we can get at the graph, and then we can get in the simulation. Okay. After that, I want to explain about the calculation. Okay. About the calculation, I forget to write the T max. Okay. The T max is 1378.8. Okay, that is the value of the T max. After that, we can see about the how to find the efficiency of the machine. Okay. The efficiency, we must to find the P in and P out, and then we multiply with 10%, 100%, and then we get the efficiency. Okay. What we can get from the simulation is PSC, only PSC. But in the PSC we can get the P in. How? Okay. PSC, what I've shown at the PSC is 1.429 E plus 06. That's mean 1.429 multiply 10 power of 6. That is the meanings of that value. Okay. From that we can calculate, but we want to know what the P in that is right or not. Okay. How to calculate that? This one like this. Punca we can get the punca 3 P in equal punca 3 multiply with 382 multiply with 1857 multiply cos 0.85. 382 is the V line, 1857 is the I line. Okay, then we calculate, then we get the 1049 600. That is the exact value for the P in. But we just want to know the how to get, or how to get if she did not show the PSC. For the P out, we can get that HP multiply with 746. That means one horsepower equal with 746 watt. So what the lecturer give to me is give to our group is 200 horsepower. For the 200 horsepower, we multiply with 746, we can get the P out. The value of the P out is 149.2 kilowatt. Then we can find the efficiency. The efficiency is P out per P in multiply with 100, and then we got the efficiency is 10.013%. That is the efficiency. Okay. Thank you.